Hi, I'm Sunil Yu, and welcome to my talk on the age of AI and how we can delay the building of Skynet. I'm the CTO for an AI safety startup called Gnostic, and I used to be the chief scientist over at Bank of America, where I've put a good amount of thought into the topic of AI. And my goal in this presentation is to actually walk you through some of those thoughts. Now, in the title of the presentation, I mentioned the age of AI, but you probably thought I meant that we're in the era of AI, but actually, I mean something else. So before we get started, here's a question for you. If you were to put a human age to today's AI, what would that age be? Now, given whatever age you may have determined, here's the follow-up question. What type of weapon would you be willing to give it? A sharp pencil, scissors, knife, a gun, a bazooka, a speeding car, nuclear launch codes? Well, there's a lot of talk about topics like artificial intelligence, generative AI, machine learning, automation, and so on within the security industry. And we're oftentimes led to believe that these capabilities will like totally revolutionize our security practices. But I think we need to be conscious of the limits of these capabilities before we start entrusting them with matters of importance. Well, today I'm going to discuss how AI and automation are distinct and how they fit together through decision making. Many people, I think, combine these capabilities and use these terms almost interchangeably, especially for letting the machine also do automated decision making. And it's easy to fall into this trap. But I think doing so can be quite dangerous and create many unintended consequences. So before we let machines do automated decision making, let's understand the limits of these capabilities. And let's also understand what is the age of AI. So I'm going to use a combination of multiple frameworks, and I plan to show you how we can determine how far AI is advanced and how to understand it when it might be appropriate to actually connect it to automation, do automated decision making. And these frameworks, I think, will help us understand and answer some of these basic questions that we have, such as like what's the difference between AI and automation? How separable are those functions? How mature are these capabilities, and how mature do they need to be for certain security relevant use cases? We've actually had a long history of epic fails when it comes to automated decision making. So, using these frameworks, what can we learn from these failures, particularly as it relates to security? And then, lastly but not least, given the current level of maturity in these capabilities, what kind of guardrails should we be considering? So, I'm going to cover these questions through some of these frameworks that I'm going to share with you now. The first framework that I want you to consider is the OODA loop, or at least a slightly modified version of it. When we look at most security stacks, they actually have all four of these components: sensing, sense making, decision making, and acting. Now, sensing requires sensors, which is the collection of telemetry from these sensors, and we want to be able to get that telemetry to a point where that data is usable. Sense making is where we have analytics, and this is also where AI and machine learning go. Next up is decision making, and this is where we take the information, and then based on our knowledge and wisdom and judgment, we hope to make the right decisions that define the next courses of action. And then lastly, in acting, you have the actual execution of that decision. Now, if we use this construct, then it becomes clear that artificial intelligence is distinct from automation. And there's this decision-making function that connects AI with ML. And so I think it's important to consider these separately. When we conflate these terms together, we also risk connecting these capabilities together without a mature decision-making framework, which then I think results in severe and unintended consequences. So this first framework is intended to explicitly call out that the function of decision-making, which separates out sense-making from acting, exists, and we don't want to forget that step. And just to put it in context, let me offer a story that I think most people are already familiar with, which is, of course, Skynet from the movie Terminator. Now, you may not remember the specific details of why Skynet was created, but I think it's instructive to understand how the original goals for Skynet actually fit nicely into the OODA loop as well. So look at, for example, the sensing and sense making. We look at the global information grid. There were originally there was this sensor network, and we wanted to make sense of the telemetry coming from that. We also wanted to make sure that it can act on these sensors. In the movie, they gave Skynet control over lots of military hardware and things that can basically kill us. And then on the decision-making side, well, they gave the power of decision-making to the machine because we wanted to remove human error, and humans were too slow, right, to be able to react to various things. Well, what was it that we're actually trying to react to? Well, it turns out it was a security use case that we were trying to react to. We wanted to respond quickly to enemy attack, and so, isn't it interesting that we essentially, in the movie, built Skynet to address what is essentially a security problem? So, anyway, that's the first framework to think about where we are in the age of AI and how we think about how we delay the building of Skynet. So, but let's look at the next framework. The next framework is from DARPA, and it gives perspectives on what specific factors drive higher levels of capability as it pertains to AI. Within DARPA's framework, there are also four components, and they partially align with the OODA loop. The first factor is perceiving. It's essentially how well a machine can consume large quantities of data about the world and it's essentially understand what's going on. So that's sensing and a little bit of sense making. The second factor is learning. So that's how well can a machine take the information and start adapting to that environment. And this is squarely in sense making. The third factor is reasoning. How well can a machine decide on what to do next, and explain why it made that decision? And that is squarely in decision making. And I think we should note here that DARPA calls out decision making separately from the other functions, but it still bundles it all within the context of AI. And then the fourth factor is abstracting. How well can a machine take what it has learned and apply it to an entirely different domain? Now, there's not an analog here with the OODA loop, but note here that, again, DARPA doesn't include the action itself or the execution of the decisions as a part of AI. Now, as we evaluate using the framework, the DARPA's framework, as we evaluate different forms of AI, one thing to be mindful of is we want to understand how far along it is on the spectrum between zero to human level. And so we'll see this progression across three waves of AI. So the first wave is based on handcrafted knowledge. This has a little bit of perceiving and lots of reasoning. And the examples they give include things like tax preparation software and chess. The Cyber Grand Challenge that they ran many years ago fits into this category. And the capabilities in this wave rely heavily on the handcrafted knowledge of experts who can basically codify the decisions that they've made and codify it into software and provide pretty deterministic outcomes. So, for example, in like TurboTax or tax cut, any sort of tax prep software, it will take basic inputs in various forms and then make highly deterministic decisions over them. And you can say like first generation Sims kind of perceive their world using common event formats and reason over this data using various alerting rules that we've handcrafted. And these capabilities fit into this first wave pretty well. The second wave has a lot of perceiving and learning capabilities. And the second wave is pretty much where we are today. Machine learning and what most people call AI is in this particular space. Now, the second wave can do some amazing things to find patterns similar to what's been seen previously. And this pattern recognition has been really useful to develop capabilities like voice recognition, facial recognition, the large language models that undergird things like ChatGPT, self-driving cars or somewhat self-driving cars, hopefully that don't run over people and so on. And even the current generation of SIM products that we see today and security products that we see today are grounded in the second wave of AI. But the second wave is also very limited in its reasoning capabilities. And remember, this is where decision making lives. And again, note that DARPA calls this statistical learning. And I want to emphasize that because it's hard to sometimes sift through the hype of AI. But when we can replace words like machine learning, deep neural networks, and all the things associated with AI into statistics, it helps provide some bounds around our expectations of what these things can really do for us. Again, it can do some amazing things, but at the same time, we found that there's things that they can do that aren't really helpful either. We've seen hallucinations, and of course, there's ways that people can use statistics to lie, right? And so there's a whole book even written on this topic. And did you know that 83.7% of all statistics are entirely made up? So before we give too much credence to statistics or to AI, let's make sure we understand it's how it works from a statistical standpoint, and that helps us again manage our expectations on what we can get from AI itself as well. To understand on the statistics side, without proper context or explanation, it has limits. And likewise, systems that use statistical-based machine learning will have similar limitations. Now, they're helpful. The statistics are helpful to find similarities and to find known patterns and to fit a curve. But without proper context or explanations, the similarities may mean nothing. So here are a couple of silly examples of patterns that are similar. It turns out that people who drown after falling out of a fishing boat, that correlates really nicely with the marriage rate in Kentucky. Now, we know that's a pretty silly example. There's no causality here. But the statistical-based machine learning essentially suggests that there might be causality, but humans realize there isn't. There isn't if someone were to ask, why is this the case? There's really no logical answer because there's no causal relationship between the two. And there's a whole bunch of other, silly examples that you see here. But the point is that we know that these are absurd, unexplainable correlations. But why do we know that? And how would a machine know to be able to know that as well? And that's one of the core challenges that we have in the space around security and AI as well. When we apply these techniques to security problems, we encounter similar challenges. And there's a great paper on the use of machine learning for network intrusion detection that was written way back in 2010, and it was well before all the recent craze that we've seen around AI. This specific paper talks about why it's so fundamentally different and significantly harder to apply machine learning to security problems. In a nutshell, it distills down to the differences in the nature of the problems that we see. In in the environment that we're in for security, it's not a closed world. And machine learning works really well in closed worlds where things are bounded and the rules don't change very often. However, the internet and many enterprise environments that we're in are unbounded environments, and the rules change all the time. And furthermore, attackers are constantly trying to change the rules and pervert the rules through novel attacks. But machine learning isn't really great for finding true novelty, especially in open environments like the internet. And so, many things end up being outliers, which is why we end up with so many false positives when it comes to machine learning. And when we try to tune our ML models, we recognize that the costs and the consequences for a false negative are pretty high. And so, we don't end up wanting to misclassify a real attack as being normal. And so we end up accepting a huge false positive rate. But anyway, as we try and ensure that we don't have any, we end up with new problems just because of the volume of issues, alerts that it causes, which usually ends up costing lots of analysts time. Now, we should also be mindful that, any vendor in the space that makes a claim about machine learning and the product will state that they have very few false positives. But, this is a play on words. They mean that everything that they alert on will be an anomaly. But that doesn't necessarily to them, that's not a false positive, but for all intents and purposes, for us, because it's costing analysts time, we will count it as a false positive, because it's essentially consuming cycles that we don't necessarily have. Anyway, ultimately, we need these systems to find malicious anomalies because if there's a malicious anomaly for which we know there's a pattern for, then the machine learning algorithms are able to find those. But again, because things are oftentimes operating in an unbounded situation, it's really hard. It's really hard because these environments that we have change all the time, shift all the time, and end up being not the tools that we have for machine learning end up not being as useful to find things that are novel. Now, there are places where things like generative AI is actually useful. And for that, let me offer a model that I created called the Cyber Defense Matrix. It's a simple model that characterizes the 5 functions in this cybersecurity framework and 5 different areas of interest from the standpoint of attack surfaces. Now, generative AI is pretty useful for a couple things, but the main goal for any artificial intelligence tool that we have is essentially to displace the blue portion that you see on the bottom. Now, with that said, I don't think generative AI will address or displace all the aspects of the people side of the cyber defense matrix, because one thing that generative AI is useful for is actually anything that requires creativity. And if there's a particular function that requires creativity, like threat modeling or discovering vulnerabilities, vulnerability research, then I think that's where it's going to shine. But any place where it's going to need a deterministic outcome, that's where statistical-based machine learning which may have varying types of outputs, which you saw earlier in the second wave, statistically may be impressive, but individually may be unreliable. It may not be suitable for functions within cybersecurity that require a deterministic outcome. All right, so let's move on to the third wave. So the third wave, which for the most part we have not reached yet, is what DARPA calls contextual adaptation. Here we have similar perceiving and learning capabilities as in the second wave, but we see much better reasoning and abstracting capabilities. What this means is that for the third wave, we should expect to see systems that can explain its learning and decisions, ultimately leading to a clearer understanding of causal factors, not just based on statistical correlation. And ultimately, a system like this will give us a better understanding of why it classifies something as malicious and why it's okay. And this provides more predictability than when a system succeeds or fails or drives towards more trust. Ultimately, it allows us to drive more trust into a system. And with security, we really want that trustworthy aspect of systems. We've seen attacks where with some small perturbations, we can have a system classify a stop sign as a speed limit sign. But if you asked an ML system why it thought it was a speed limit sign, you would struggle to get a comprehensible answer in the second wave type of systems. But at this third wave, such a system should be able to say, hey, this is why it's a stop sign. It's because it's red, it's octagonal, and it's at an intersection. And so these simple explanations, these explainable outcomes is what we should see in the third wave of AI. Now, this notion of reasoning, I want to define as well. Because if you looked at ChatGPT back when it first got released, you would have noticed something interesting about its claims around reasoning. And if you looked at this output here, you would think that it's reached the third wave of AI according to DARPA. But what's also interesting is that come mid 2023, they got rid of the visual representation of this claim, and they just basically say they have that this has advanced reasoning capabilities. If you were to even ask ChatGPT itself and say, hey, do you think it's in the third wave? Well, again, you can only trust ChatGPT up to a certain point, but even ChatGPT itself wouldn't say that it would fully qualify as being part of the third wave. So despite what it seems to be impressive reasoning abilities, it actually does not have the level of reasoning that is expected for the third wave, according to DARPA. Okay, so that's the second framework. And then we go to the last framework. And the last framework is actually based on classical education. So when it comes to the maturity of a decision-making framework, this is actually a pretty good one. We used to homeschool our kids. So in the process of learning how to teach kids, we also learn about this thing called the classical education trivium. And it lays out the progression of how kids learn. First, you start out with the grammar stage. This is where you soak up facts and raw information. Think of it as the roots and the trunk of the tree. It sets the foundation for everything that grows above it. Next, you go into the dialectic or logic stage. And here, it's like the branches of the tree. It connects facts together and compares the truth of opinions to determine what's logically correct and what's not. And this is also when kids can really start explaining why and how one truth connects to another truth. And then the last stage is the rhetoric stage. And this is when kids grow in wisdom and can convince and persuade others, and they can integrate various subjects together and disciplines together. Now, if you remember, according to the DARPA framework, the ability to explain why and how happens in the third wave, which means we're not quite there yet. And now, if you match these three stages of childhood learning to actual ages, you get this breakdown where during the elementary school years, the focus is primarily on grammar with a little bit of rhetoric and then a little bit of dialectic. And by the way, this is also why they call some elementary school grammar schools. In junior high, we focus more on dialectic, and then in high school, we focus more on rhetoric. But note again, if we need machines to be able to explain why and how, and our current technologies aren't able to do that adequately, then we have to realize that our machines haven't quite left elementary school yet. So think about that for a moment. What kind of decisions are you comfortable in delegating to kids at that age range? And to frame it one other way, and to tie this back to the OODA framework, when we compare these components to the abilities of children versus adults, we can see why we may want to take precautions when giving decision-making and acting abilities to machines. Looking more at the comparison, consider that the decision-making engine for children is the amygdala. Now, the amygdala is fully developed at birth, and this decision-making engine is driven by things like fear, emotion, impulse, aggression, and instinct. But for a fully grown adult, the decision-making engine is actually the prefrontal cortex, and this is generally fully developed at age 25. And by the way, if you've ever wondered why you can't rent a car until you're age 25, that's your hint there. Anyway, it's towards the forehead, and basically it controls behavior, meaning that you can avoid having a tattoo in your forehead that says poor impulse control. It can also prioritize inputs and provides that impulse control that we're talking about. Now, an amygdala for decision making engine might be fine if one's sensing and sense making are clean and unpolluted. But let's look at that as well. I think for children, we have very questionable inputs like their peers, memes, social media. Now, for adults, we may have similar inputs, but we've developed filters and better discernment for those inputs. And then for our sense-making algorithms, well, anyone who has a teenager can probably agree with me that their sense-making might not make that much sense. But for adults, we should expect them to be rational and logical and to be able to explain their logic. So consider now, with the current level of maturity in our machine learning systems and the type of hostile sensory inputs that we get from the internet, and with that unexplainable logic, what kind of decisions should we be allowing machines to make? To understand how we can gain that confidence, now let's look at some scenarios or some lessons learned from the past to determine how we can get that confidence and trust in our systems, even if some of the elements that make up that system are not fully mature. And as a way to represent what happens when we lack maturity of a certain capability, I'll depict the lessons learned as like skipping steps in the sensing, sense making, decision making, and acting process. So when we skip steps, we're going to need more guardrails. So, jumping from sensing to acting is going to require a lot more guardrails than sensing, sense making to acting. And again, if we go through the whole sequence, then fewer guardrails are needed. So anyway, let's look at each of these scenarios from the angle of the security world and what kind of guardrails that we might need for each. So here's a situation where it's just sensing directly to acting. This is essentially like a reflex action. So this is, stimulus response type of system. The stereotype for this is the threat intelligence sharing, where in the past we would get intel from someone saying, go block this, and we would, without question, go block it, only to shut ourselves off from the internet or block sites like Google or Facebook. This sort of reflexive action has resulted in really bad outcomes in many cases. And so the things that we learned from this was to have guardrails to ensure that the sources that we have are trustworthy and reliable, to ensure that whatever actions that we take are going to be very narrowly scoped so that we don't cause more damage than necessary. We also want to make sure that there's a way to stop the action as quickly as possible and as much as possible to also have something that makes it reversible too. So those are some of the guardrails that we learned when we skip the sense-making and decision-making steps. All right, next we realize, okay, let's put some sense-making in. And so this is a situation going back to threat intel when we would say, okay, let's do some regression analysis and determine, have we seen this in the last X number of days? Do we have different systems that can issue a verdict on this being good or bad? This is essentially what tools like VirusTotal do for us. And through the mistakes that we've learned here, we've realized that it's very helpful to have, again, multiple points of view and to do lots of regression testing to ensure that things have as much as possible a deterministic outcome. Do they continue to operate as is expected? Are there things that stop working or unexpectedly stop working as a result of that? Now, in other programs that I've seen with DARPA, here's an example of a program. It's a cybersecurity related program where we can map 3 of the 4 components of the OODA loop. And as you'll see, it's actually missing the decision-making component. And the absence of a clear decision-making step should serve as a warning sign. This program intends to do sensing and sense making and then immediately jump to protective measures or acting. And as the chief scientist at BAE, the folks who are running this program states, they want to leave behind a trail of logic for the decisions um, so that they're, whatever decisions are made implicitly or explicitly, we want to have this trail of logic so that humans can follow up and ensure that those decisions are correct. And so again, that's one of the guardrails or lessons learned that we have here. Ultimately, as we look at other situations where we've had failure points, we want to ensure that there is a clear, as much as possible, predictable outcome. And where we can have documented assumptions about what needs to happen, and those assumptions are understood, the outcomes are understood, and the ownership of those things are understood by the operators, then we can skip the we've had situations where we can skip the decision making step, but again, having these guardrails in place are super useful. And then even when we have all four steps in place, again, we need to have some additional guardrails here as well. Everyone's already familiar with the Colonial Pipeline shutdown, but I think one of the things that we should learn from that is what sort of threshold do we want to establish before anything bad happens, where we can have a clear understanding of the trade-offs between taking no action from the results of the action that you take. And we again, the story around the Colonial Pipeline is well known by many people, but I don't know if the consequences of those actions were clearly understood. One of the classic studies on this was back when DoD shut off the internet, the NIPRNet, during the Code Red virus attack. And they didn't realize that when they shut off the NIPRNet, all of a sudden you couldn't control the locks on the Mississippi River. And so there was a cascading set of disruptions as a result of that. So again, having an understanding of when these having understanding of these thresholds of taking no action versus action is something that we want to establish as a guardrail. And again, also to have a clear understanding of who's going to be accountable for the actions that are being taken and the outcomes associated with those as well. All right, so now taking all these different lessons learned and the frameworks that we talked about before, I want to go back and ask the question, try to answer the question from earlier. What is the age of AI? How mature is it today? And so if we look at it from these three frameworks, I think we are still not quite out of the grammar stage. With AI, again, I put it in the sensing and sense making part of the OODA loop. DARPA would say that it doesn't quite have the reasoning abilities, but it has great perceiving and learning. And then using the classical education framework, again, it's not able to answer the questions of why and how yet, but it's getting pretty close, right? And I think as we get closer and closer, we want to make sure that we have clear understanding of what guardrails we want to have before we start connecting artificial intelligence to action. Okay, and so as a summary, here's 6 guardrails that I've developed or I've learned through my experiences to say, let's make sure that these guardrails are in place, and to have a really conscious, deliberate sort of chasm between AI and automation, because we want to make sure that we understand what we're getting ourselves into when we make that leap. So these sort of guardrails are things, again, just to reiterate, make sure that the inputs are trustworthy. Make sure that you have a wide range of diverse inputs. Make sure that you have as clear as possible an understanding of the assumptions that go in and the processes that will undergird that. Make sure that you have you can operate in bounded conditions. Make sure that if you're operating in unbounded situations, then you're asking for lots of trouble. So try to narrowly scope things and do lots of regression testing as much as possible. Have a kill switch ready. Make sure that you have a way to shut the automation down. If possible, also have a reverse gear. How can you undo actions that are taken? Know what the thresholds are. Make sure that you know when inaction is potentially worse than taking action. And then make sure that there's clear lines of authority there as well. These sort of things are necessary because I think as much as we think that the age of AI is still at the grammar stage, one thing you realize when you have kids is they grow up fast. And so that's something that I think we may be seeing sometime soon. If we look at the progression of AI capabilities over the last several years, we see this incremental growth. Things don't seem to change, improve very much over the last few, as the model gets larger. But what's really interesting is more recently, we started to see as models get larger, unexpected emergent abilities emerging as well. And this sort of spike in the curve is kind of represented, is perhaps better represented in this way. And this is thanks to a friend of mine over at Team 8, Gal, who showed these kind of curves. But this perspective is um, over the last, in the early stages of AI development, we had this trade-off between performance and having it being general purpose. And we expect it to curve to grow gradually upwards as you continue to have the model get larger and larger. But since about 2016, 2017, we started to see that curve bow a little bit outwards. And this was unexpected. This was not the ability for the model to actually get better as it gets significantly better, both in performance and being general purpose, was an unexpected surprise. And so the warning here, I would say, is we're getting closer and closer to a very capable, mature system. But right now, it's still not quite there. And so my proposal is, looks like we're on this inevitable march towards building this very capable system. But let's wait till it turns 25 before we start connecting it to things that might kill us. So with that, thank you very much, and here's how to contact me.